Lesson number 84 is about multiplication of radicals and functions. Now our first problem is to simplify 4 times the square root of 3 times 3 times the square root of 2. Now the key thing to know in these problems is that we want to multiply our constants together, the numbers out in front, then we want to multiply our radicals together, then we'll simplify to find our answer. So 4 times 3. If we take our 4 times 3, that's our first part. Then we're going to take our radicals, and that's going to be the square root of 3 times the square root of 2. So we're going to get the square root of 3 times the square root of 2. We're just reorganizing everything. Remember, the order of multiplication doesn't matter. 4 times 3 is 12. And 3 times 2, the square root of 3 times the square root of 2, that's the square root of 6. And we get an answer of 12 times the square root of 6. With 12 times the square root of 6, we can't simplify the square root of 6 because that would just take us back to the square root of 3 and the square root of 2. So we've got our final answer. Let's take a look at a few more. Here we have to simplify, and in this one we need to use the distributive property. So first we'll multiply 4 times 5, and then we'll multiply the square root of 3 times the square root of 2. We'll actually show the multiplication in our next step. Then we're going to multiply 4 times 6, so this is adding, and the square root of 3 and the square root of 3. Now as we go through, 4 times 5, that's 20. Square root of 3 times the square root of 2 is the square root of 6, so we get 20 times the square root of 6. That can't be simplified anymore. So then we're going to add 4 times 6, that's 24, times the square root of, well, square root of 3 times the square root of 3, that's the square root of 9. And we know the square root of 9 is the same thing as 3, so we're going to get 24 times 3, because this can be simplified since the square root of 9 is a perfect square. And we'll go ahead and find our final answer in our next step. So 24 times 3, it's like saying the number of hours in 3 days. That must be 72 hours. And we've got our 20 times the square root of 6. That hasn't changed at all because it can't. And we've got our final answer. 20 times the square root of 6 plus 72. Let's move on to another one. This one looks similar. So we've got 4 times the square root of 2 times 3 times the square root of 2. 4 times 3, that's 12. The square root of 2 times the square root of 2 is going to be the square root of 4. We're going to add then, and we're going to get 4 times 5, because we take the whole numbers or the constants by themselves without the radicals to multiply. 4 times 5, that's 20, times the square root of 2. Now let's simplify. The square root of 4 is 2, so we get 12 times 2, plus, well, there is no perfect square for the square root of 2, so we just leave it. And then we get 12 times 2, that's 24, so we're going to get 24 plus 20 times the square root of 2. We've got our final answer, and that's a fine way to leave it. Doesn't matter if the radical is out in front or in the back. Or another way to say it is the constant can be first, or it could be last. We could also say 20 times the square root of 2 plus 24. Remember, order of addition doesn't matter. The second part of this lesson is about functions. And functions are relationships between the input, which is called the domain, or more typically called the x, and the output, or the range, which is the y, in which every input has only one output. Now that's the key here. Every input has only one output. Okay, so every time you have an x, it can only go to one y. Does a diagram designate a function? Well, if it designates a function, that means every input has only one output. The 4 goes to the 7, the 5 goes to the 2, the 6 goes to the 14. This is our domain on the left, the x values, and this is our range on the right, the y values. Can you think of another name that we could call the domain and the range in terms of variables? Well, another way that we could say this was, this is the independent variable, and this would be the dependent variable. And I'm just going to write var for variable over here next to the independent variable. Just another way that we can name these sets of numbers. So, does a diagram designate a function? Yes, because every input only has one output. So the answer here is just a simple yes. Let's look at another one. Does a diagram designate a function? It's asking, does every input domain only have one output, range? The 4 goes to the 2, the 5 goes to the 7, and the 6 goes to the 14. Each input only has one output. So our answer again is yes. This is a function. We've got a couple more. Does this diagram designate a function? Well, here the 4 goes with the 2 and the 14. So does every domain only have one range, or does every input only have one output? No. This is not a function because the 4 goes to the 2 or the 14. So this would not be an example of a function, even though the 5 only goes with the 7 and the 6 only goes with the 14. The 4 goes with the 2 and the 14, so that makes it not a function. Got one more. Does a set of ordered pairs designate a function? So we've got our x first and our y second. 4 goes with the 6, 7 goes with the 2, 4 goes with the 5. Hold on. We've got a 4 going to a 6, and then we've got a 4 going to a 5. We can't have an input going to two different outputs. So no, this does not designate a function. If you wanted to, you could build a set of numbers like we had before. We've got a 4 and a 7 as our inputs. And our outputs would be 6, 2, and 5. And the way that this would look if we did it that way would be the 4 goes with the 6, the 4 also goes with the 5, and the 7 goes with the 2. So you can see the 4 goes to two different places, and that can't happen in a function. So the answer here is no. Our lesson practice will be on page 349. Make sure you got your notes complete, and I'll see you during our next class.